Hey everyone. Another case that we often encounter when we have linear regression models is natural logarithms on both the independent variable or one of the independent variables or the dependent variable. So in this video I'm going to talk quickly about, briefly about how to interpret models that involve independent or dependent variables with natural logs, right? So again we have a case with a continuous dependent variable and a continuous independent variable and potentially some additional control variables. And we have a natural logarithm in one of those variables. So we have three different cases, of course. One is we have a logged independent variable. So there's just a natural logarithm on x1. We can have a logged dependent variable, so a natural logarithm on our y, or we have a logged independent and dependent variable, so log y and log x1. Okay, and so in each of those cases, the interpretation is slightly different from our basic linear regression framework. The reason is that as soon as we have a logarithm, the effect on the original scale, so x1 and y in the non-logged scale, so to speak, is not constant anymore. Similar to the quadratic case where we had changing marginal effects across ranges of x, we have changing marginal effects across ranges of x as soon as we have the logarithm of x or the logarithm of y as well, right? And so here are three examples of how to interpret these coefficients that involve natural logarithms. And just kind of as a quick reminder, or to remind yourself of how to interpret those, whenever something has a natural logarithm, that either the change in that variable or the change in that variable always can be interpreted or switches to, rather than a 1 unit change, it changes to a percent change in some way or another. And I'm going to talk about how specifically in a second. Right? So if we have a logged independent variable, so x1 is logged rather than on the original scale before we run our regression, then the way to interpret this is holding everything else constant, a 100% increase rather than a 1 unit increase in x1 is associated with a beta 1 increase or decrease in the expected value of y. Right? So now all that changes here is that compared to the case where x1 is just included as the original variable, it's not a 1 unit increase. Beta 1 doesn't tell us something about the 1 unit increase or the change in y that is associated with a 1 unit increase in x1, but a 100% increase in x1, right? And so to understand why that means that the marginal effect is changing across values of x, I again simulated some data, and we have here a model with a continuous dependent variable y and just one independent variable which was logged. So log x1, the coefficient here is 0.77, right? So again, this is a regular scaled continuous dependent variable and a logged independent variable. So this 0.77 is can be interpreted as the change in y that's on the original scale, the change in y that is associated with a 100% increase in x1, right? And so why is that the case, or how do we interpret this? This means that depending on where you are in x1, this is now kind of just plotting this logarithmic fit. If you're here at x1 equals 5, a 100% increase in x1 means moving x1 from 5 to moving x1 to 10. That's a 100% increase in x1 from 5 to 10. And that 100% increase in x1 leads to a beta 1 increase in y, or is associated with a beta 1 increase in y. So this change here, that's 0.77 on the original scale of y. Right? So moving from 5 to 10 leads to a 0.77 increase in y. Similarly, if we now move from, if we're now, suppose we start at this point where x1 is equal to 10, a 100% increase in x1 is not moving from 10 to 15, but it's rather moving from 10 to 20. I should actually move myself a little bit too, so that you can see what's going on. All right, so again, we started here. This is beta 1 or x1 being equal to 10. A 100% increase in x1 means moving x1 from 10 to 20. And that move, that's a 100% increase in x1, and that again has a beta 1 or is associated with the change in y of beta 1. So again, the change in y here is 0.77. So as you can see, that means the larger the values for x1 get, the smaller the marginal effect of x1 on y becomes, right? So the 100% increase here is, of course, a larger increase on the original x1 scale that leads to the same change on the y scale. Okay, and of course here, as from 1 to 2 or something like that would be the same effect as well, right? This holds everywhere on the across possible x1 values, right? So this shows you that, again, involving this logarithm leads to kind of a non-linear relationship between y and x, and the variable in our case, now the independent variable being logged, means that change is now can be interpreted as the change in y that is associated with the 100% increase in x. Okay. The intercept, by the way, that's another important thing in this case when we have the logged independent variable. So we take the log of x1, of course. When we talk about the intercept, that's the expected value of y for x1 being equal to 0. And of course, when we return this back kind of to the original scale of x1, the log of x1 is equal to 0 for x1 being equal to 1, right? So the intercept here in this logarithmic fit is the expected value of y for log x being equal to 0, which is an equivalent of saying x1 being equal to 1, because the log of 1 is equal to 0, right? So the intercept here that we estimate this alpha parameter, that's the value, the expected value of y for x1 being equal to 1 rather than 0, because the log of natural log of 1 is equal to 0. Okay, that's another subtle change, but in most cases, we're not so interested in the intercept anyhow, but this is an important difference as well. All right, when we have a log dependent variable, this changes a little bit. So this was just the graph for a logged independent variable and a dependent variable on the regular scale. The logged dependent variable, the image is kind of slightly different in the sense that now we interpret this as follows: holding everything else constant, a 1 unit increase in x1 is associated with a 100 times beta 1% increase or decrease in the expected value of y. Okay, so suppose that these and I didn't prepare a graph for this one, but suppose that these coefficients were where x1 was actually on the original scale and y was logged. Then what this is supposed to explain is that, or what this means is that this effect of 0.77 would be interpreted as a 1 unit increase in x leads to a 77% increase in y, right? So now the change in y is a percentage depending on where we are in y. So it's kind of, you could think of this as a similar graph, where just the percent that is basically just flipped, right? Now we have a 1 unit increase in x that has a percentage change effect on y, on the y scale, okay? Here the dependent variable is logged, and so we have a 1 unit increase in x because x is on the original scale that is associated with a percent change increase or decrease in y, and the percentage is 100 times the coefficient. So 0.77 would mean a 77% increase or decrease in y. Since it's a positive, it would be a 77% increase in y. So every 1 unit increase in x increases y by 77%, depending on where the value of y, of course. Now, when we have a logged independent and dependent variable, then both have to be interpreted as percentages, so to speak, right? So as soon as we have kind of this type of log-log model, both y and x are logged, we interpret this as follows. Holding everything else constant, a 1% increase in x1 is associated with a beta 1% increase or decrease in the expected value of y. So now both x1 changes in terms of percent, and the coefficient is the expected change in y, again in percent. And that's because both the dependent variable and the independent variable are logged. Okay. So again, all of those kind of cases lead to nonlinear, non-constant marginal effects. Effects change depending on the level of x or the level of y. They're always relative to where you start from, just as in the example that we kind of talked about here. And therefore, they can kind of help us model these nonlinear relationships or relationships with decreasing or increasing marginal returns, marginal effects. Okay. Last quick note about natural logarithms. 2 questions that might be on your mind as you're watching this video. One is, when do we actually use these logarithmic transformations? When should we actually apply these logs? And in general, one thing to keep in mind is that the logarithm, of course, is only defined for positive values. So whenever you have an x variable that takes on negative values or takes on 0, then you have to be careful, because if you take the logarithm of those variables, all those values will ultimately be missing, right? So in general, it's not advisable to use logarithmic transformations for continuous variables that can take on negative values, right? Oftentimes, at least in political science, of course, we have variables that are strictly positive, so those can be used with a logarithmic transformation. And it oftentimes can be useful to use this logarithmic transformation as soon as we have variables that are, one, strictly positive, as I mentioned, and that are highly skewed. So where we have very extreme or skewed distributions, because ultimately those can lead to skewed error terms in our skewed residuals, which is something we want to avoid in our regression models. Secondly, so when the distribution is skewed and x and y are strictly, or x or y are strictly positive, then it might make sense to consider a logarithmic transformation. Similarly or relatedly, when x and y have very extreme values or outliers, the logarithm basically allows the estimates to be less sensitive to extreme values, right? And so the underlying reason is, of course, for example, if we have a logged x here, that, as you see, for very high values of x, kind of where the marginal effect of a 1 unit increase of x decreases. Okay. So when we have extreme values, it can be useful to use natural logarithms as well. There are some, rough guidelines and not really strict rules, but there are certain data types that you more often see being logged versus not logged. So for example, whenever models include things like wages or firm sales or market value or population sizes across countries, for example, or enrollment numbers, things like that are often skewed, often have extreme values. So those variables, if you have models that include those types of variables, oftentimes a natural logarithm or logarithmic transformation is being used. Other variables where we usually don't see a logarithmic transformation are things like education, or if you have percentages, or any type of quasi-continuous variables, right? So especially with survey data, we oftentimes have Likert scales or scales that range from 0 to 10 that are not strictly continuous, but just have 10 or 7 different categories, but we treat them as quasi-continuous. And so as soon as you have these quasi-continuous variables, usually we don't want to apply logarithmic transformations. In most cases, that is not advisable. So keep those in mind as guidelines. Of course, they're not strict rules. It's not forbidden to not to take the log of a population, but oftentimes it makes sense. And of course, we talked about model fit. Ultimately, the guiding principle, if you compare those models, should be the relative fit. Using the logarithmic transformation or not using the logarithmic transformation. All right, in the next video, we'll talk about dichotomous dependent variables rather than continuous dependent variables.